Hi, my name is Mitch Fulton, and I'm a PhD student in the Advanced Medical Technologies Laboratory at the University of Colorado Boulder. Today I'll be presenting our research on comparing visual odometry systems in actively deforming simulated colon environments. First, let's talk a little bit about the motivation behind this research. Colorectal cancer is currently the second most deadly cancer in the United States, with around 150,000 new cases and 53,000 deaths expected by the end of 2020. However, if caught early, colorectal cancer has over a 90% 5-year survival rate. To screen for colorectal cancer, the most common procedure is known as a colonoscopy. As shown on the right, this procedure consists of the colonoscope being inserted into the anus, progressing through the rectum and colon until it reaches the cecum. A visual inspection and biopsies are then performed using the light, camera, and other tools while the colonoscope is being removed. But since this is a purely visual inspection subject to the physician's colonoscope steering capabilities, how can physicians and patients be sure that the colon was effectively screened? Today, the most common colonoscopy quality metric in use is known as the adenoma detection rate, or ADR, which is inversely correlated with colorectal cancer. Roughly, this measures what percentage of patients a physician finds adenomatous polyps in when they're having their first colonoscopy inspection. So, this is really a long-term measure of physician quality, not procedure quality. It's also dependent on other factors such as patient demographics. Intra-procedurally, or during the procedure, the only feedback shown to correlate with the ADR is the length of time taken to perform the inspection. However, 4.3% of colorectal cancer cases are from interval colorectal cancer, or cancer that's found after a negative screening within the past 5 years. This suggests that some polyps or cancers are not being found, as they're often hidden behind the structures within the colon, known as haustral folds. An effective intraprocedural quality metric could help alleviate this issue, and we believe that real-time mapping could be that metric. It could show unseen areas as the map of the colon is built, so the physician could re-inspect these areas during a procedure and make more accurate diagnoses. To map and localize the camera within an environment, a technique known as simultaneous localization and mapping, or SLAM, is often used. Much research has been done on this, and SLAM is often considered to be a solved problem for static, well-textured environments. However, for environments such as those seen in the colon that are dynamic and deformable, highly reflective, and low texture, SLAM is yet to be a solved problem. This lack of algorithm development could be due in part to a lack of open source data sets with ground truth representing an in vivo environment. Currently, there are either open source data sets for SLAM, such as the Kitty dataset shown in the top left, or segmentation tasks within the colon, such as the Kvasir dataset shown in the bottom left, not both. Therefore, in this work, we have established a dataset with positional ground truth that combines these kinds of datasets into a SLAM dataset, including many of the difficulties of the colon environment, including deformation, occlusion, spectral highlights, and low texture. As an overview, we used a colonoscopy training model as our simulated colon environment, recorded the data with ground truth, then tested 4 SLAM and visual odometry systems on the sequences: OrbSLAM2, DSO, LSD SLAM, and SFM Learner, or Structure from Motion Learner. These 4 systems were chosen because they represent 4 different ways to approach the SLAM problem: sparse indirect method, sparse direct method, dense direct method, and a learning-based method. We then analyzed their accuracy and failures on the sequences. To collect our data, we used the Kyoto Kagaku colonoscope training model as our simulated colon environment. The simulator was affixed to a felt-covered board with Velcro rings for stability throughout the data collection process. To collect and record the data, we built a data collection platform consisting of a small endoscope camera and LEDs for lighting at the end of a long aluminum rod. The acrylic mount housing the camera and LEDs also held the magnetic sensor needed for the ground truth data. This sensor and a magnetic source emitter, parts of the Polhemus Patriot magnetic motion tracking system, were used to provide ground truth positional data for each of the sequences. A magnetic system was used as it does not require line of sight and is more accurate or does not have the attenuation of other non-line of sight methods. Due to the constant magnetic field emitted for ground truth, both ferrous and non-ferrous metals, including stainless steel and aluminum, cause noise in the ground truth readings due to paramagnetic effects. To measure the noise introduced into the ground truth data by the paramagnetic effects of the data collection platform, we fabricated a noise characterization test fixture. This fixture consists of an acrylic board with a ground truth grid, Delrin supports, and nylon screws to hold it all together. To collect noise data, we first calibrated the system by positioning the magnetic field emitter so that its readings without interference aligned with the ground truth grid. We then inserted the magnetic sensor into the data collection platform and took readings with the sensor at each grid location in a variety of orientations. Using this data, we reduced the parameters to a distance, r, and a coincidence angle, theta, or the degree to which the data collection platform is aligned with the magnetic field emitter. Using the error between the ground truth positions of the board and the readings, the noise was fit to a function and corrected for each of the sequences, reducing the maximum ground truth error from 35 millimeters to 5 millimeters. With the data taken, we were then able to run the SLAM systems on the data sets to analyze their accuracy and failures. For each system, the parameters were kept at the default values as these were found to produce the best results, and the best of 3 estimates was chosen. The first shown is LSD SLAM, the direct dense method. Next is ORB-SLAM 2, the indirect sparse method. Last is DSO, the direct sparse method. Note that structure from Motion Learner is not shown in this video as it does not produce a global map. For each of the sequences, the causes of failure were analyzed. Different sequences highlight different causes of failure with more prevalent difficulties. In sequence 1, due to some rapid or non-smooth camera motions, motion blur is present. In sequence 2, there are many rolling shutter effects, which causes distortion in the images. Sequence 3 has severe occlusion, causing the most difficulties of the analyzed sequences. And finally, sequence 4 has deformation in spectral highlights, which hinders feature matching between frames. While each of the sequences has all of the shown difficulties, the most frequent ones to appear in each are shown here. Despite all these difficulties shown, the most common failure was a failure to initialize, which appeared to be due to an inability to find unique features and feature matches. This failure of initialization also restricted analysis to sequences 1 through 4, as not all of the systems could produce an estimate for sequences 5 through 7. With all of the estimated trajectories calculated and the ground truth data corrected for noise, the estimation's accuracy was able to be calculated. First, a global trajectory alignment was performed between each estimate and the ground truth trajectory. Then the relative error was used, which is the absolute trajectory error calculated over all the trajectory subsets of a chosen length. The equation is shown in the bottom right corner. Shown here are the translation error statistics as a percent of trajectory subset length from this calculation across all trajectories. Also shown is the ideal maximum error, which was estimated to be the amount of error that would allow the trajectory to stay within the colon. Note that the translational error decreases over longer subtrajectory lengths. This is due to the scaling and alignment done on each of the trajectory estimates being global, so the longer subsets are more optimized for ground truth accuracy. Shown here are the per sequence translational error results as a percentage of trajectory subset length. As different difficulties are more present in each sequence, the performance of each system varies across the sequences. We also calculated the rotational relative error, and the results are shown here. As you can see from the equation in the bottom right, this is calculated very similarly to the translational relative error. The ideal max was again estimated to allow the trajectory to stay within the colon and was 10 degrees. Unlike the translational error, the trajectory alignment and scale optimization does not take the rotation into account, so the rotational error grows over longer subtrajectory lengths, as can be seen here. Like the trajectory error, the rotational error also varied greatly across the sequences for each tested system, with different systems working better on different sequences. In this talk, I have presented a new open source data set in a colon environment with ground truth data. In addition to this data set, in the future we would like to create another open source data set of in vivo colonoscopy videos with ground truth data. We hope to achieve this using a similar technique presented today, but in a clinical setting. We also plan to use this and future data sets to develop better SLAM algorithms for this environment, and hope it will be useful to the research community to do the same. Finally, we plan to explore combining machine learning and traditional SLAM techniques to create more effective localization and mapping for in vivo environments. With that, I would like to show the references used in this paper and for this presentation. And I'd like to thank my lab and our funding sources for supporting this research. If you have any questions, email the contact information or visit our website. Thank you.